Good morning, afternoon, and evening, everyone. Today, we, Group 2, are going to talk about linking seismic measurements to the International System of Units. But before so, firstly, we're going to talk about calibration in a laboratory. A calibration in a laboratory enables the determination of a sensor's properties under well-known conditions and with estimated measurement uncertainties. The basic principle of calibration is the same for all motion sensors. An excitation of the wanted quantity is generated, and the output of the sensor is then compared to a well-known reference. In the case of the dynamic calibration of rectilinear accelerometer, velocity sensors, which also include seismometers or displacement sensors, the exciter is often an electrodynamic shaker, also known as a shake table, generating sinusoidal excitations. Now, as you can see on the screen, it's primarily calibration using laser interferometry as the reference, ISO 16063-11. Primary calibration of seismometers relies on a laser interferometer as the S.Si traceable reference, with displacement or velocity derived directly from the laser wavelength in meter and timing reference in second. Under sinusoidal excitation, displacement and velocity can be related directly in the frequency domain without numerical integration or differentiations. So during the calibrations, the exciter shakes the sensor with a known sinusoidal motion. The interferometer measures the true motions. The seismometer output is recorded at the same time, and by comparing both signals, we find how the seismometers respond in magnitude and the phase. Seismometers cannot be calibrated like accelerometers. They must stay upright, they are very sensitive to small motions, they are often very heavy, and low frequency does require long measurement times. Horizontal exciters may bend under load, causing tilt, which become a major error at low frequencies. This is why seismometer calibration requires more careful design and control of the setup. There is no universal rule on how to mount seismometers during calibration, but they should be lightly strapped so they don't move, but not rigidly fixed. The laser must be aimed at the sensor feet, not the housing, to avoid measuring unwanted resonance. And large seismometers may need several measurement points. As you can see on the screen, several dedicated calibration facilities exist, such as PTB, CEA, Spectra, TPLA, Japan, Italy, and USA. And PTB has developed multi-sign excitation to reduce measurement time at very low frequencies. However, multi-sign methods may reduce cross factor and signal-to-noise ratio, increasing uncertainty. As you can see on the screen, secondary calibration is a method where a seismometer is calibrated not with a laser interferometer, but by comparing it to another reference seismometer whose calibration is already known. The setup is similar to primary calibration, same exciter and sinusoidal motion, but the main difference is the reference device. Because the reference seismometer already carries uncertainty from its own calibration, secondary calibration always leads to larger measurement uncertainties compared to primary calibration. The sensor under test or SUT and the reference seismometer are mounted together on the exciter. Both sensors record the same sinusoidal motion. The calibration works by comparing their outputs. Two analysis methods exist. First one is classical sign approximation. It's to extract amplitude and phase from both sensors using curve fitting, and COPA, coherent power method, a more robust method for noisy or low frequency conditions. COPA uses the cross spectral density between SUT and reference. This ensures amplitudes are real, valued, and based only on the coherent part of the motion shared by both sensors. Secondary calibration can be performed using two practical methods. The first one is direct comparison. The SUT and the reference record the same motion. Their output radio then combined with the non-calibration of the reference gives the SUT sensitivity. It's considered more simple and accurate when the reference is stable. Second one is substitution method. A working standard stays permanently mounted on the exciter. It is periodically calibrated against a transfer standard, and the SUT is then calibrated against the working standard without changing the setup. This avoids downtime and is ideal for repeated routine calibrations. In low frequency range such as 10 microhertz to 20 Hz, multiple sensors can even be calibrated simultaneously using the same reference motions. Next is issues when calibrating in a laboratory. Laboratory calibration aims to determine the properties of the seismometer under test. However, during the development of in-laboratory calibration procedures, several issues specific to seismometer were observed. This issue must be considered both when designing calibration setups and when estimating measurement uncertainties, because they directly affect the reliability of the calibration. First one is tilt. An ideal exciter should produce a perfectly rectilinear motion. In practice, however, the excitation tilts slightly during displacement, causing a small change in the directions of motion. Even this small angular deviation can produce significant errors in the seismometer's output, especially at low frequencies where displacements are large and excitation amplitudes are small. Tilt also changes the local gravitational acceleration clock acting on the sensor, further affecting the measured signal. The measured acceleration in a horizontal axis becomes, as you can see on the screen, so even tiny tilt angles cause large errors at low frequencies. For example, at 10 microhertz with 1 mm per second excitation, a tilt of only 1 microrad over the displacement introduces a 16% measurement error, and this error is not detected by the laser interferometer. Therefore, exciter tilt must be evaluated before calibration and results must be corrected accordingly. Next is electromagnetic influences. Some seismometers are sensitive to changes in the magnetic field, producing output even when no real seismic motion is present. The sensitivity depends on the sensor design, the internal displacement measurement technology, and the materials used in suspension springs. Such electromagnetic effects especially impact low-frequency performance, increasing sensor sensitivity by up to 10% below 0.1 Hz. Therefore, the electromagnetic environment around the sensor must be considered, and, when necessary, the magnetic field should be reduced during calibration. In the S.Si exciter used at CEA, the actuation system generates magnetic trace fields around and above the exciter. Measurements show that field decreases with distance. A compensation coil, a ring supplied with adjustable DC voltage, was implemented to generate an opposite magnetic field. This reduces residual field near seismometer, so it no longer affects the calibrations. Next one is temperature sensitivity. Broadband seismic sensors are designed to minimize temperature effect, and in field installation, they are often protected with passive thermal insulation to stabilize performance. In a calibration laboratory, such insulation cannot be applied because the sensor must be mounted directly on the exciter. As a result, temperature sensitivity may still appear if ambient temperature variations, both amplitude and time constant, affect the sensor during calibration. Therefore, the quality and stability of temperature regulation in air-conditioned calibration labs must be considered, especially when the regulation cycle duration is comparable to low-frequency calibration times. Next one is excitation levels and environmental noise. Calibration laboratories typically contain technical equipment such as electrodynamic exciters, amplifiers, HVAC system, and operate within active building. This results in higher environmental noise levels compared to remote seismic faults. For technical reasons, such as minimal exciter displacement, feedback control needs, and digitizer or reference resolution, the excitation level used during calibration are higher than those experienced in normal field operation. So far, there is no indication of problems unless the sensor under test exhibits nonlinear behavior, meaning that its sensitivity changes with excitation level. Force compensated seismometers are known to be highly linear and component with compliant element would show similar relative effect and different excitations. Non-linearities would appear as higher harmonic components in the sensor output, which would not be present in the reference signals. And that's all from us. Thank you for your attention.